right, over the whole ring. Actually, I'm going to integrate it over half the ring. Why? Because I'm going to say another piece here will cancel with another piece there. This piece will cancel with that piece. This piece will cancel with that piece. So I'm going all around the ring. This piece, and I doubled it. This piece, this piece, this piece, this piece, this piece, this piece. Right? When you're these two pieces, see the gravitational field they create is like this, and then their x components only add up, right? Then you keep doing this. So you're integrating over half of the ring. Over half the ring. So then what you notice is that all of these terms are actually constant. So you don't have to integrate anything because neither the x changes or the r changes as you go around the ring. Okay? So then everything comes out of the integral. And you just get integral of dm over half the ring. Well, integral dm is just equal to m. So since you're integrating over half of the ring, integral dm is going to be m over 2. Half the mass of the ring. So m over 2. And then that 2 and this 2 will cancel. And then so you have the general equation. There it is. G of x is equal to g mx over r squared plus x squared to the 3/2 power. Okay? Now when I get a general equation like that, sometimes there are certain things I can do to see if the answer makes sense. For example, I can find out what the gravity would be right at the center and see if what answer I get makes sense, right? So limit, so g of 0 is going to be what? Well, if I'm right at the center, that means x is 0, and then x is 0, so that means it's just going to be 0, right? So then I can ask, does that make sense? If you're right at the center of a ring, basically you weigh nothing, you just float. Is that right? The answer is yes, yeah, because the ring is equal distance away from you. All parts of the ring attract you, right? So yeah, you're going to weigh nothing at the center of the ring. It should be. Okay? How about the, as you go farther and farther away? The limit of g of x as x goes to infinity. So then we want to find out the behavior of the g function as you get farther and farther away. So then if I get farther and farther away, how do I find the limit of this? We use one of the tricks we use is to say, as this gets bigger, this becomes insignificant compared to that. So we can kind of ignore the effect of this, right? Because as x gets bigger and bigger, let's say x is equal to 10 times the radius. 10r squared is going to be 100r squared. 100r squared plus r squared is 101r squared. Right? So then this doesn't affect this as much. Right? So then the way to find the behavior of that function is just to say gmx over, then you ignore the r on the bottom. You just say x squared to the 3/2. So what is that equal to? X squared to the 3/2, the 2 cancel x cubed, and then you have what? Gm over x squared. And you can see my smiley face. That's perfect. That means my integration was correct. Why? Because as you get farther and farther away, the gravity of the ring should look like the gravity of a point mass. The ring doesn't look like a ring anymore. Right? So if we were to plot the strength of the G field as a function of x, here's what's happening. Right at the center, the G field is 0. As you get farther away, the gravitational field is increasing in strength. Right? right? Gravitational field is increasing strength until you reach a certain point somewhere. Then it starts to decrease, and as you get farther and farther into infinity, it decreases as a 1 over x squared function. So its behavior should be 1 over x squared. Proportional to 1 over x squared. And which it should, right? So there's two ways to analyze and see if these answers are making sense. One way is what we just did. Find out the limit as x goes to 0, the limit as x goes to infinity, and then try to plot the strength of the G field of the planet, like this, right? And then see if it's making sense. As you go to infinity, it's behaving like the point mass. The other thing to do is to plot what the gravitational field of that object will look like. The gravitational field it creates in space. So what kind of field should it create? So it's probably going to look something like this. It's going to come like this. It's coming from infinity. Remember, there is no gravitational field that's going out, because there is no gravity is always attractive. So gravitational fields always come towards they're pointing towards the object. So it comes like this. And then the same thing on this side. You see? So where is the spot where the gravitational field is the strongest? Where is that spot here? You see? Well, wherever the field is the most concentrated, right? Somewhere here. See, so this one where the field lines are the most concentrated is the strongest point of the gravity. That's where you would weigh the most, right? As you go this way, what happens? The gravitational field gets sucked into the different parts of the ring. You see? So imagine the ring like this, goes like this, like this, like this, like this, like this, like that, like that, like that. So that when you're at the center, the gravity is 0. There's no gravitational field line going through you when you're at the center. So you weigh nothing. You have to step a little bit to the side in order to weigh something. You see? And so what happens as I start zooming out though? Imagine this was a computer screen and I could zoom out, zoom out, zoom out, zoom out. What would happen? Well, you wouldn't see this section anymore, right? You have to really zoom in to see this section. If you zoom out, it will just look like a dot. The ring will look like a dot, and then it will just be like this. I mean, the arrows are this way. Is that kind of hard to see why it would look like that? If you zoom out, the ring begins to look like a point charge. I keep saying charge, point mass, right? And then when you zoom out, all the field lines, you see here, all the field lines are coming in radially. So when you zoom out, you don't really see that the field line is coming and then bending. See? You don't see that bending thing. It just looks to you like they're just coming in radial. Well, that's what it means to say when you go out to infinity, the gravitational field looks like a gm over x squared. That's the gravity of a point mass. So when you go out to infinity, it just looks radially coming in, right? And then you don't really even see the bending down there. It doesn't matter to you. You just see, oh, okay, that guy looks like a point charge. Now if I zoom in, zoom in, zoom in, zoom in, then I can see. Okay, then that's different. Down inside over there, there's something else happening. You see. So then that means the answer we got was right. Okay, so then if we wanted to, could we find out where that location is that creates the strongest gravity? Yeah, we could, right? How would we do it? We would go back to the equation that we derived, find out what x is required to maximize the g. Well, how do we do that from calculus? Find out the derivative of g with respect to x, right? How do we get that? Quotient rule we have to use. This times the derivative of that. Is it this times the derivative of that? Minus this times the derivative. Is it the derivative of the
derivative of the numerator times the denominator minus?
Oh, okay, yeah. So then the GM doesn't matter, it's just a constant. So the derivative of the numerator, which is just 1, times the denominator minus the derivative of the, it's going to be the numerator times the derivative of the denominator, right? 3 as times the derivative of the inside over the denominator squared. As you see, all of that calculus you have learned, why did you learn it? All the trig, all the everything. Linear algebra and differential equations. You learned it to apply to physics, to physical type of situations, right? So, okay, then we can factor out the x squared plus r squared, right? So then you have your then once you factor this out, that disappears, and then you have here what? R squared plus x squared minus the 2 and the 2 cancel, 3x squared. And that's all really matters. This part doesn't even matter to me, because I'm going to set this equal to 0 to find out what x is that gives you the maximum. And then so you're going to have here r squared minus 2x squared then equals 0. So beautiful, I love this. Go crazy. So that means if I want to draw a nice picture of the gravitational field lines, here's a very good zoomed in picture. If this is the radius, r over root 2 should look something like this, right? So the gravitational field should come You see? So the point of most concentration is r over root 2. You see? So if this is the radius of the ring, this is roughly r over root 2. So that's where they come, and then they start bending outward. By the time you get to the center, there's no field line. The only one weird line is this one. This one that comes this way, where does it go? Does it bend down or does it bend up? I think it just kind of goes like this and then just ends right there. There's another one that comes like this and ends right there. Okay? So it doesn't bend anywhere. It just comes like that. The other ones come and bend up, you know. Yeah, cool. Okay, so now we can answer any kind of question. So let's see if we go to the if we go to the rings of Saturn, let's say. D-ring, C-ring, Maxwell gap. Those are all the frequency gaps in the ring that are clean of debris. Those are resonances. Maxwell gap. So later when we talk about waves and resonance, sound wave and resonances, you can kind of see the connection with this. There's resonances in the rings of Saturn, and in the asteroid belt there's resonances. So those resonances create spots where there is no ring. Same as with the experiment you're going to do with the sound waves, right? D-ring, C-ring. So let's just take, for example, one of the rings. All these gaps, right? The Huygens ring, the Huygens gap, the Russell gap, the Kuiper gap. Those are all resonance gaps. Beautiful, amazing. Okay, let's say we take the way that it's been named is that it's not necessarily named from the first. Like the A-ring is not the closest one. The A-ring is the first one that was discovered, so it was probably the brightest one. Then the B-ring was the second one that was discovered, so it's kind of named after the discovery. So the A-ring is probably pretty bright and big. So the distance from Saturn's center, 122,000. So that would be the radius of the ring, right? So the A-ring radius would be, let's just say something like 130,000 kilometers. 130,000 kilometers. I'm just averaging out the radius, right? And then the mass would be what? They give you the mass. We click on it maybe. Oh, so total mass of the rings is 1.54 times 10 to the 19th kilogram. So they're not really that heavy. Okay, let's just estimate something. It's kind of hard to find. It's probably embedded somewhere there. So 1.5 times 19. So let's say something like 8 times 10 to the 18 kilogram. Something like that. I'm going to estimate. Okay, so then we can say, okay, g of x is gmx over x squared plus r squared to the 3 halves, right? So we could find out for Saturn's A ring, what's the maximum gravitational field it creates, right? G max. What would I have to do? Well, remember that maximum gravity is created at the location x is r over root 2. So then I would put here x equals r over root 2. So gm r over root 2 over x squared plus, then what I would do is r over root 2 quantity squared. So that would create the maximum gravitational field, right? Gm r over root 2. Then over here you would go r squared over 2 plus r squared to the 3 halves power. Right? Because r over root 2, you're squaring that, you're going to get r squared over 2. So then here you're going to get gmr over 3 halves, right? 3 halves r squared to the what? 3 halves power times root 2. Then you're going to get gm r over 3 halves to the power 3 halves right? So it's like 1.5 to the power 1.5 okay? Times root 2, and then r squared to the 3 halves is going to be what? R cubed. Then this cancels this and you get r squared. So that is the maximum gravitational field you create. Gm over 3 halves to the power 3 halves to the times root 2 times r squared. Okay? So then now we could put in the numbers. G max 6.674 times 10 to the minus 11. Now I can put the mass of the ring, 8 times 10 to the 18, over, right? 3 halves, I'll just write it as 1.5 to the power 1.5 times root 2. Then the r squared is going to be the radius, but you have to change it to meters, right? So 130,000,000 squared. Whew, a lot of stuff there. Okay, let's take the calculator, put that all in. .674 times 8 divided by 1.5 to the power 1.5. 1.5 to the power 1.5 divided by root 2